desks. You can do the desk thing if you need a desk, pull a desk up. I think they're all right-handed desks, unfortunately. Might be some lefties mixed in. No, they're all right-handed. I'm sorry. Apologies. There's plenty of room. You can spread out and take two of them if you need them. So the reason I had you freeze your butts off outside was because I knew it would be easier to get you to freeze and then come in here, rather than bring you in here, then you go back out and come back in. So I figured just get out of the way, get the paint out of the way first. And I wanted to collect some more data. More on that momentarily. After we talk about today, the exam for next week is going to make a lot more sense. So there's the exam that's posted. Part of the exam deals with linear modeling. I think part of it does deal with grade. Yeah, part of it deals with grade, Mackenzie pass ride. And part of it deals with Usain Bolt and his distances and times when he set a world record in the 100-meter enduro sprint that he did in, I think it was Berlin in 2009. And today's discussion is going to lead directly into you understanding that a lot better. So that's the last part of the exam that you probably, if you've looked at the exam, that part won't make sense until today. Today will make sense. Today, after we chit-chat today. And this is going to take some time today between the data collection and between the analysis. So the point of today, well, you'll see what the point is as we go through. We have the groups. You got all your data? Let's collect it real quick. Let's collect it real quick. We're going to put it in here. All right. I'm going to clear out this data. This is the last crew's data. And the last data we had was actually, the last data we had, I did it up at Grandview's Hill, which I think is steeper than down here, but I didn't want you to hike up to Grandview just to do that. And I couldn't get a room in Grandview, so it didn't help anyway. Sorry. Sorry, it's colder than I thought it was going to be today. Okay, so 0 feet, that's all zeros, and zeros across there. We're going to use this to collect some data, and we're going to have some, we did 5 trials, right? We did. This one too. Well, with the 6 was a practice. We didn't count that one. Unless you want to. You think we should count that one?
The first one?
Should we count that first practice trial?
Sure.
What the hell? We'll put it in and look, and we'll see. We'll see. All right, so 0. So practice, give me the 25-foot, folks. Just give me all of your times. Tommy, Don, go ahead.
Yeah. 3, 3.1, 3.11, 2.93, 2.87, 3.06.
All right, a little bit of variation there. I love that. So what I've done up here, Chris, you can see it better. What I've done up here is I've given 3 columns. Averages, medians, and deviations. We'll talk about all these as we go. The idea of what we just did, the reason we did it multiple times is because there's stuff called error whenever you do an experiment. There's things called error. And error sounds like a bad thing. You think about error. Error sounds like you screwed up. But error happens. I mean, if I gave everybody in here a coin, which we will do probably next class, and have you flip it a bunch of times, suppose I gave you a coin and told you to flip it 10 times. How many heads do you think you're going to get? Half the time, right? Because I mean, all you're going to get 5 out of 10. No. But what's going to happen? On average. On average, you'll either get 5 out of 10. But some of you might get 4 out of 10. Some of you might get 6 out of 10. Some of you might get 8 out of 10 on that first roll. Somebody today at 244 got 10 out of 10. That's error. The error is that not every single person gets the average every time, but the numbers average to an average over time. That's kind of the point of error. So what we're going to do is, the reason I do so many trials is to try to get an idea of where my true value is. I'm not really sure where it is. Again, I don't do this experiment frequently enough to keep track of exactly my times. But I get an idea with some consistency or lack thereof. All right, 50 feet, folks. Fire away.
Okay, their practice was 5.03.
Excellent.
Number 1 was 4.66. Number 2 is 4.75. Number 3 was 4.94. Number 4 was 4.75. Number 5 is 5.
Thank you. And I was trying to be as consistent as I could on my end. I always started, and you might not notice, with my left foot down on the cranks. I didn't pedal forward. I let gravity pull me forward, if you will. So I started with my left pedal down, and then I lifted my foot up. You probably saw me doing this at the top. And then, that's because I was on my phone, lost my face. And then I put my pedal on, and then I dropped down. I wanted to drop down more quickly, but I couldn't do that. For some reason, not going fast enough, I tried to do that, I was going to fall over. So I tried to be consistent with what I was doing, but even though I was being consistent, there's slight deviations in the time, which are probably minimal and can be taken care of by averaging them at the end of the day. Thank you, guys. Next up, 75 feet.
5.91.
All right, 1.
5.78.
Okay.
5.84.
Oops. Hang on 1 second. Not 45. Go ahead.
5.81. 5.60. 5.82.
Thank you, Shelby. There we go. There's my time at 75 feet. How about at 100 feet? Go ahead.
I have 6.93, 7.03, 7.03, 7.15,
I want to brag.
6.84, 6.88.
Excellent. Excellent, excellent. Thank you, guys. 125. Or about 100? That was 100. 125?
8.09,
8.09. Okay.
8.12, 7.82, 7.6, 7.84, 6.75.
Beautiful. 150.
8.16.
Oops.
That was the practice I did this one.
That was practice? Yeah, that's good.
8.43. 8.49. Oh, excuse me, 44. Right.
Okay.
8.44.
I totally got this wrong, by the way.
7.97. And then the other two we didn't have.
Oh, that's okay. We can let that go. That's the beauty of taking the averages and the medians, is that even with those, its chances are they're going to be close. So these are fairly consistent. We're going to leave them at that. 175.
Oh, I have them right here.
Excellent.
9.36,
Okay.
9.81, 9.62, 9.45, 9.03, and 9.25.
All right. And last but not least, at 200.
Yes, we've got 10.52, 10.15, 10.30, 9.5, 10.34, and then 10.5.
All right. So that 9.5 seems a little bit low, but you know, again, variation in the samples. So I'm liking the idea. If you look at that scatter plot there on the right, I'll pull it so it's bigger. Although it's like 10 feet tall, it's kind of big already. But I've got, in that scatter plot, I've got the medians and the averages graphed. I forget which one is which, but they look pretty similar. If I use the word average and median, hopefully that doesn't throw you off too much. What is an average of a bunch of data?
The average of all of them added together.
Add them all together and then
Divide by how many?
divide by how many you've got. So for most of those, it's add up 6 numbers and divide by 6. Good. What is the point of doing that? Why do you take an average of numbers?
Accuracy.
In what way? I like that. It's Tony, right?
Yeah.
Good. In what way? Accuracy. I like that.
You just, like you said, you might have variation, like the 9.5 at the bottom is probably not correct. So
Good.
it takes those ones out.
Okay, good. Suppose Tom has, let's just be silly here, 3 books. Tony's got 1, and Tony has 7. On average, how many books do they have? 3, 1, and 7. On average, how many books do they have? 3 and some change, right? We got 3 and 1 is 4 and 7 is 11. 11 divided, oh, it's 2 and some change actually, isn't it?
3.3 something.
Oh, it's 3 and some change. 3.33333, 3 and a third, huh? 3 and a third? Okay, so what does that mean, 3 and a third? If we took all the books they had together and spread them out, say that again, evenly, so they all had the same amount, that's the number they would all have. So in other words, the average times you see up there, if you took all the times it took me to do this over all the trials and spread them out evenly, it would spread out evenly to about 3.01 seconds. That's the idea of those averages. I know how we do it. We add up and divide by how many they got, but the whole point of it, it's kind of like it's called an equal share measure. Take a whole bunch of numbers, it smooths it all out so that every single data point has the exact same. So when you take an average, realize that's what you're doing. Realize that's what you do. I like the accuracy argument. I do like that very much. The idea of it, though, is to kind of like egalitarian. Now, there's a problem with that. There can be a problem with that. Do you know why averages can sometimes be misleading? Give you an example. This might make you realize what it is. Indiana State University, I'm going to guess 1974, 1975, Indiana State University released a brochure. They said the average starting salary of a bachelor's degree holder in business from Indiana State University, on average, is $10,000 higher than any other bachelor's degree in America. Statistically speaking, in the 1974 year, they tracked all their graduates from Indiana State University, and they tracked their starting salaries, the business majors, and they averaged those numbers together, just like we just did. And that average was $10,000 higher than any other school's averages from the bachelor's degrees, from any other school. Why?
It's suspect.
It is very suspect, but they were using it for recruitment. Why was it suspect? Say that again.
A couple people did really well.
One person in particular, who graduated from Indiana State University, did not use his degree in business, went on to play professional basketball for the Boston Celtics by the name of Larry Bird. He was a business major, and they just so happened to factor his MBA salary into the computation. Were they lying? No. Is it a smidge bit misleading?
Yes.
Just the tiniest. So, if you have what are called, you know what Larry Bird's salary would have been called in that data set? Very nice. It's called a statistical outlier. 243, we analyzed them at great depth to decide how big too big is. His average was too big, or his salary was too big to be included. So for example, if on one of these trials, I was doing, 8.1, 8.4, 8.4, 7.97, 21.5, we'd have to wonder, what the hell happened with that? Did somebody forget to push stop? You don't want to include that data point, obviously, because you want to analyze, there's something suspect about it. Good. That's one way to deal with it, is to microanalyze the data. The other way is to use what's called the median. What is the median? You may have heard this before. Middle number when you do what? I love that. Good. Put the numbers in order and pick the number in the middle. Now, you might notice that all of our numbers have, there's 6 of them. So there really isn't technically a middle. You have to go halfway between the middle numbers. So what Excel does in the medians column over there, move this just out of the way a little smidge. What it does to calculate these values is it looks at the 6 numbers or the 4 numbers, and it finds the middle 2 and finds the number between the middle 2. So let's just do one real quick. Suppose we look at these guys right here. That's the smallest one, yeah? Next biggest is that one. Next biggest is that one. Then that one. Then that one. Then that one. So those are the 2 middle ones, yes? Between 10.3 and 10.34 is 10.3. What's it saying there? 2, I should hope. It's not saying 10.32. It's saying 10.3 for whatever reason. But that's the idea. That's what it's calculating. It's calculating the middle number between those 2. That's what the median is. The median's nice when you have the potential for an outlier data point, because it won't treat that outlier data. It won't treat Larry Bird as a $10 million a year player. It'll just treat him as the highest value. So the fact that he's 10 million, 1 million, 100,000, or 10,000 doesn't matter. It's just that he's the largest one. So you can see, suppose this number right here was not 10.5, but was 100.5. Would the average change? Would my average? Hell yeah, it would go up, wouldn't it? Would my median change? Not one bit. Because it wouldn't look at 10.5. That's not the middle number. It would throw that out and look just at the middle ones. The reason, why would I do both? Why would I graph them both on that scatter plot? Be brave, my friend. To see if there is any difference, right? What do I see over there? It doesn't appear that there is a whole lot of a difference. It looks like the averages and the medians are the same. I don't see any difference at all. So that's why I do both at the same time, to see if anything. There's a smidge of a difference right here. These guys right here, and maybe a smidge right there. I think that's arguably the same. Just throw that out and call it good. So you guys pick. We're going to do medians or averages. We can make the averages look nicer if we can round them down to more usable numbers. What do they call this? The 3.01 and 4.86. Because technically speaking, I think your stopwatches only give you 2 decimals of accuracy, don't they? Hundredths of a second. So we should knock those down to hundredths of a second. 5.79, 6.98, 7.7, 8.25, 9.42, and 10.22. There's going to be our, we'll use that for data. We'll not throw it in. Good so far? Right. Now here's a question for you. Why the hell did I make you do that? Why did I make you do this? Why would I make you stand out, freeze your butts off and your fingers off on a Monday morning to collect data of me running my bike down a hill?
Find the slope.
What would the slope tell me? I love this taunt. Good. We can find the slope. Let's take a look at that data. Take a look at that data. There's our data. Let me remove the medians from the chart, shall we? Let me remove the medians. Pull the medians out. Move. Okay. There's just the averages. Okay, the medians are the red ones, I guess. Does that look like linear data to you? Arguably, it looks linear, doesn't it? I mean, if Tom's going, well, maybe it looks more curvy than linear, curvilinear, or curvy than linear. So let's have some arguments as to why we think it might be linear. Well, first of all, it kind of looks it. I mean, if you think about it, it ish looks linear. It starts here, and you can envision if you remember, it starts at 0, 0. If you think about it, and it looks, you can put a line through that. Best fit line would be kind of like that. It would definitely miss 0, 0. That's a bit of a problem. But if you ignore how we collected that data, you might be missing something big in the analysis. What's a good reason why it might not be linear? Remember, this is how much time I've gone.
Is it because you're gaining speed?
Boom! It might not be linear, because linear would be like my distance covered if I'm like holding the brakes going down that thing. If I'm governing my speed, you ever been in a car with a governor that you can't accelerate past a certain speed? Okay, you can't just like slam the gas and keep going faster and faster and faster, because eventually you get to a speed above which you cannot go. Well, I could make my data linear outside if I was holding the brakes to a certain point, holding my speed consistently. But I was letting the hill pull me, if you will, down the hill. Now, it wasn't perfectly sloped. It did kind of flatten out towards the bottom, but there's not many places on campus with 200 feet of unbridled joy of careening down. Iowa Street, one of these days. Take you guys up to Iowa Street. You'll see some death. But the point is that since I'm probably getting faster as we go down, I wonder if we could argue this isn't linear. Let's think about this. Let's think about it. I'm going to turn this off for a second. I want to go to the chalk. It's actually a chalkboard measure. That's making me happy. Hopefully there's chalk. Okay, there's a button on here somewhere. Blank. Blank. All right. Watch it. This is great. Prejudice, power. Not in this class. Propaganda. Vehicle for ideology. Protest. Love this. Now, what I want to do is I want to discuss why our data, that's okay, that's not bad, might or might not be linear. Okay, so this whole class started with the idea of mathematical modeling. What's the point of modeling? In a modeling in a mathematical sense is what? Tom, go, please.
Just a tool to predict the future.
Excellent. It's you look at the behavior of data, and you say, okay, here it's behaving a certain way. Let's develop an equation for that, and see where the equation points later. Good. Or even, if that's extrapolation, we can also interpolate with it. I actually want to interpolate with our data. We'll come back to that momentarily. So far, the only kind we've looked at is linear. That's the first kind we've looked at. Now, what makes data look as though, dude. I've not done that in about 15 years. Sorry, guys. What makes data linear? What makes it, please, Amber?
Well, that it's kind of all the same. I mean.
In what way?
faster
Rough
at the
it.
end.
Good, so that's a vote for maybe my data is not linear. Good, but supposing we had linear data, for example, the uninsured rates from last class, if you do the quiz for Wednesday, the Facebook number of words per privacy policy over the past few years, what's the keystone of linear data? What remains the same? I love when you said the same. What remains the same? Tony mentioned it earlier.
The slope.
Boom! The slope of the data. Now, it's not going to be perfect, but it's going to be arguably, on average, the same. You're going to have data that looks something like that, where essentially, if you look at the slope between sets of points, the slope on average is fairly consistent. You've got rises, and you've got runs. Such that the rises over the runs are essentially consistent. Ish, the same. Now we know they're not going to be the same, because if they're the same, that's when the one-armed man, the fugitive, comes and tries to kill you. When your data is too perfect, something's wrong. But when you see essentially a trend in well-behaved data, then you're like, okay, this is starting to look fairly decent. With me so far? We guys buying this? We're buying this. Okay. I think that might be a problem. That might be a problem with our bike data. Because if we look at it again, I wonder if I can put it on. See how this looks without the screen down. Blank, yeah. Nope, zero. And. You got nurses in here, right? I gotta tell them drugs on my head before the day's over. Check it out. Now notice, the data is going to be a little bit backwards. The way I've placed it on the axis is probably not the way you think to place it. I put the times on the horizontal and the distance on the vertical because time is generally a very good independent variable. Okay, if we did it, you could do it the other way too, it's totally fine, but it makes more sense not to. The reason I did it the other way, the way I did it this way, is because now, if we talk about the slopes of this, which I do want to talk about, Tony, I want to talk about the slopes of this data. We're going to have the rises, which are measured in feet, distance, which is feet, over the runs, which are measured in seconds, time, feet per second. What does that sound like? What does that sound like? Jacob, say it louder.
Velocity.
Velocity. AKA speed, AKA something we actually care about. Because what do you think the question I want to answer is? How many miles per hour was I going when I passed, where are my 200-foot marks, people? 200 foot. How fast was I going when I passed Jacob and his crew? Guesses. 18. Love it. 18. Other guesses. 15. 15, Chelsea, 12, 5, crawling. 30! I hit 52, not in Oregon, in Delaware. No, I hit it coming out from Bachelor too. Which a little bit by Bachelor, it's surreal going that fast on a bike. It's crazy. In Delaware, there was one hill in Delaware that drops you very steeply. And it's surreal. Wasn't on 52, so 50, anywhere from 12 to 30. So the question is, I can approximate that using this data, but we have to do an analysis first. We have to get a good model first of all. It's going to be an interpolation, not an extrapolation, which makes me trust it more. But I have to get a model first in order to do it. So the question is, can we rule out this being a linear model? Well, let's think about it. If it were a linear model, we'd have to have a fairly consistent rise over run. So for any given second, we'd have to pick up roughly the same amount and Amber's like, no, we can't assume that at all, can we? Because
we're going way slower at the beginning.
in the beginning, I'm covering a very little bit of distance over a given time. At the end, I'm picking up much more distance over less time. Look at the spread outness, that's a technical term. of the data points here versus the data points here. Right? It's taking much less time to pick up these incremental, now I've got them broken out by 25 fingers, 25, 50, 75, 100. It's taking less time to pick up those 25-foot increments at the end than it is in the beginning. So we have to throw the linear model out. We have to throw the linear model out. We need a new model. Anybody have a vote? Tom had a vote. He drew one in the air, kind of like this. Because it does appear to be doing that, doesn't it? It appears to kind of be curving upward. We have a couple choices for that. There's a few choices that do that based on what you guys learned in your previous math courses. Jacob, give me an idea. Exponential is one of them. Give me another idea. Quadratic is another one. Any other ideas? We got an exponential, we got a quadratic. I'll tell you what, let's take 5, get some air, get some water, right? Warm your hands up, continue to do so. Let's compare and look at both of those and come back and decide which one we should use for this. And then we'll do it. Then we'll actually do some analysis. Cool? Thank you, friends.